Take a look at section 2.3, product and quotient rules and higher order derivatives. Mainly for day one, we will focus on these couple items. One, what is the product rule? How do we use it? And second, the quotient rule. So here we go. Theorem 2.8, the product rule describes what we're going to do here. The product of two differentiable functions f and g is itself differentiable. So that's just saying the product is going to be differentiable if both f and g are individually differentiable. Moreover, the derivative of f times g is the first function times the derivative of the second plus the second function times the derivative of the first. So you'll see this as a representation of those words we just read in the second sentence. The first function times the derivative of the second, and I know it's derivative because I can see the prime symbol, plus g of x times f of x. All right? That is the same as saying, well, here's a different notation. But what I wanted to say is we could also turn this around and go, it's the derivative of the first times the second function plus the derivative of the second function times the first function. And to be honest, I tend to use this more often than I use the other one. So you'll see me taking the derivative of the first times the second function plus the derivative of the second function multiplied by the first. If you like u and v, where u is the first function, v is the second function, then it's u prime v plus v prime u. And some people like to just use that as their way of remembering it. Alrighty, so, oh, here, I guess I got it right there, the way I tend to do it. What do we have going on here? Well, I can see I clearly have two functions, f times g, or if you like this notation, you could think of it as u times v. And we're going to just follow the product rule algorithm here. So I'm going to find y prime by taking the derivative of the first. So I'm going to take the derivative of this. I don't know, I'm going to write this out, but probably only for this one. We're going to take the derivative of the first, multiply it by the second function, 3x minus 5. It's an addition sign between them, so plus. Now it's the derivative of the second function, as I can see by the algorithm, g prime of x. So I go 3x minus 5. I'm going to take that derivative and multiply it by the first function, 4x plus 2x squared. So that's just the general layout. If you want to mark underneath it, you can see that we're going f prime g plus g prime f, where this is my f function times my g function. All right, let's execute our plan. The derivative of this first function would simply be 4 plus 4x, using power rule, and then multiply by 3x minus 5. Add, now I need to take the derivative of the g function. So that looks like it's just going to be 3, doesn't it? Because I'd have 3 minus 0, so just 3. And then 4x plus 2x squared. No derivative on the f function. That is really essentially the derivative, but we are going to get this simplified because there's probably a lot of terms that will combine. So let's distribute on this first one and get 12x minus 20 plus 12x squared minus 20x. Distributing the 3 through would give us a 12x plus a 6x squared. And now this should probably boil down to 3 different terms. The x squared terms, 18x squared. Got those covered. And we've got 12, that's 24. 24 minus 20, so a positive 4x. And then the only constant term was the minus 20. There is the product rule. It's not bad. You end up most likely doing some sort of foiling and distributing. And you're probably like, well, I can remember doing this in section 2.2, the previous section. You're right, we did. And the way we handled it without the product rule was we FOILed first and created a polynomial. I'll just do that quickly here. If I FOILed first, I'd have a 12x squared minus a 20x plus a 6x cubed minus a 10x squared. Simplify it, we're looking at 2x squared. Let's get the cubes first. 6x cubed, a plus 2x squared, and a minus 20x. And now, that's what we did in section 2, when all we knew was power rule. So now we powered through with the power rule, and that was our derivative. Notice that that is identical to what we got when we used the product rule. We can work with trig functions that are multiplied as well. And why do I see multiplication? Because right here I see a joining symbol of multiplying. The remaining symbol here is going to be just like section 2.2 where we took the derivative of cosine. So that one's going to be quite easy. So I'm seeing I've got two functions. I could do the UV one here if you want. So we've got two functions. I'll identify the first with U and the second with V. The derivative, which is what d over dx indicates, take a derivative. The derivative, I'm going to say y prime on this one, is going to be u prime v plus v prime u, derivative of the first times the second, plus derivative of the second times the first. Sometimes if you just get in the habit of saying it as you do it, I think it helps commit it to memory. All right, we are taking the derivative of 4x squared, which creates 8x, multiplied by the second, which is sine of x. Add, now I need to take the derivative of the second thing, which is cosine x, and we'll multiply it by the first function, no derivative. Now we're into minus 7. The derivative of cosine is actually negative sine, but I need to simplify this. This will become positive 7 sine x. And anything that we can really do, not much. If you wanted to lead off with your highest degree term, I guess that would be appropriate. So I'm just going to reorganize just a titch. And there's our derivative. U prime v plus v prime u. Not bad, huh? All right, C. Once again, we have two functions, u times v, and I'm going to take the derivative. So my derivative, I'll do a little bit different notation, this time dy dx, which means the same thing as y prime, which means the same thing as f prime of x. All of these mean the same. The derivative of the first. Last time I didn't do this, I'll do it here because it's quite easy to... Oh, sorry, smartboard issues. Taking the derivative of that, derivative of the first, multiplied by the second. That's my u prime v, isn't it? Add it with derivative of the second, which will be our v prime, multiplied by the first. So v prime multiplied by the first. That gives me dy dx, the derivative of y with respect to x, and I need to take and execute the derivative. So 2x times e to the x. Remember the derivative of e to the x? E to the x is e to the x, and then multiplied by x squared. So I'm just going to go x squared e to the x. Just organizing it a little nicer. If you want, we could factor out an e to the x. Oh gosh, we could even factor out more, couldn't we? We could factor out x e to the x. That'll leave me a 2 plus x. Either one of these are very acceptable answers. This one, okay, so it says given H defined by showing F times G, and then it's asking us to find or evaluate H prime of 1. So essentially what we're doing is finding the slope of H of X at X equals 1, right? That's how you interpret that notation. And then the other interesting thing, over on the right here, I'm just given lots of data. I know my original function evaluated at 1. I know my derivative evaluated at 1. I know G evaluated at 1 versus G prime, or the derivative, evaluated at 1. We will use this in our layout. Okay, so let's start out with H of X, just rewriting that statement up above, F prime G. I'm just going to shorten it up so that I don't even have the X's involved. How about that? Let's talk about doing the product rule. H prime will be F prime G plus G prime F. Notice how each function gets a derivative taken at some point. Now, let's evaluate this at 1, since that's the task that they ask us to do. So I'm going to have F prime at 1, G of 1, plus G prime of 1, F of 1. Guess where we're getting all this information? You guessed it. We're going to go up to this block of information and find the critical pieces that we need. So take your eyes here, and it's totally substitution from here on out. Substitute with the values provided. I'll call it in the table. It could have been presented in a table format. Maybe we just aren't seeing the lines, okay? There's our table. H prime of 1. H prime of 1 equals F prime of 1. F prime of 1 is 3. G of 1 is 5. Just make sure you're grabbing the right data pieces. G prime of 1 is a 7. And finally, times F of 1, which is 2. And if I want the derivative evaluated at a point, I'm expecting numeric answer. So H prime of 1 is 29. Ooh, that's a steep slope. Kind of nice. Easier to do than actually with the functions, right? Where I have to go like 3x squared plus 7. All right, here's another one. This one says, suppose the same thing. H of X is equal to F times G. Find H prime of 2. Well, what's so different about this? Well, the only thing different is the way that the data is presented. Maybe circle these, you guys. If you have a highlighter, even highlight them. Notice the pieces of information we are given. I'm given F, G, F prime, and G prime. All evaluated at 2, because notice where our red dot here is, all located at 2. Perfect, because they're asking H prime of 2. Well, we know that H of X, the derivative is going to be derivative of the first times the second plus derivative of the second times the first. You'll get that memorized, won't you? H prime of 2. If you say it while you're doing your homework on this section, it should lodge in your brain and stay there forever. At least that's the goal, isn't it? What I'm writing right now is I'm just evaluating everything at 2, and I'm just showing that piece of information. Is it totally necessary? No, not really. Is it helpful? I think so. All right, now let's execute our plan. F prime of 2. Go find my F prime graph, evaluate it at 2. Oh boy, I got to count 1, 2, 3, 4. I would say that's at a height of 4. I think this location is 2, 4. So what does that mean? That means F prime of 2 equals 4. So this is going to get substituted with its value. If you want, you could even say substitute using values from the graph. All right, so h prime of 2, we discussed how f prime of 2 was 4. I got to go look for g of 2. G of 2 is this dot here that looks like it's a 2, 2 location. So I put in 2, I get out 2. The next one is all about g prime of 2. So I put in 2, I get out 1. This is a 2, 1 location, which means g prime of 2 turned out to be 1. So I substitute g prime of 2 with a 1. And f of 2, I think you've caught this, 1, 2, 3. It looks like it's a 2, 3 location. So I want that y value of 3. When I evaluate a derivative at a numeric point, I'm going to get a numeric answer. H prime of 2 is 11. The slope of the function h, the slope of the tangent line of the function h at 2 is 11. All right, what if I have more functions? Do you see 3 functions? I do. Well, that sounds super hard. Can we do that really? Yes, we can. Kind of keep this idea that every function gets its turn having its derivative taken. I'm going to highlight, and maybe you could highlight too, every spot you see a derivative being done. Notice how what I underlined is f prime, then it's a g prime, then it's at h prime. So there's the algorithm for calculating the derivative with on functions where there's more than 2 factors. Namely, we had 3 in this one, but we could have 4, we could have 5, and the process would look quite similar. So yeah, are they a little bit of a pain? Truly, yes. So, but I've got sine and cosine that should help make this a little bit easier. So the first thing I want to do is take, let's just label out our functions here, f, g, and h. So we're going to go f prime g times h plus, give it a little space, g prime times f times h plus a little more space, h prime times f times g. Kind of like using combinations, isn't it? It's the grouping, not the ordering that matters on that. Okay, so g prime. I need to take the derivative of f. That's going to be a 2x. And then leave the other 2 functions as the original function. So 2x times sine x plus cosine x. The next one, we want to take g prime. Here's my g function. So that will be derivative of sine. We know the derivative of sine is cosine. So I'll have cosine of x multiplied by f and h. F is x squared. H is cosine. Okay, got it. And finally, we have h prime. Derivative of h would be negative sine. And then multiplied by x squared multiplied by sine of x. Kind of like the parentheses better, do you? Something like that. Is there some simplifying that could happen? Totally. It looks like they each have, they don't all have a cosine in common, do they? I think just simplify. Let's simplify. I was hoping to do a little bit of GCFing with it, but not the case. Doesn't lend itself to that. So we've got 2x sine x times cosine x plus cosine squared x squared. So I'm going to write my x squared first and then go into my cosine squared x. And then minus, I have a sine squared and an x squared. I'll write the polynomial term first and then the x squared term. It's not necessarily a polynomial there. Sine squared x. That's about as good as it gets. The one thing they do have in common is an x. That doesn't gain us much to GCF that. All right. Then that takes us into quotient rule, and I think, let me look. I don't know if that's that might be day 2. No, quotient rule is still on day one. I was just looking ahead. So let's go through quotient rule. Once again, it's a nice little algorithm. You can see how we've got f is our top function. So in this case, there's my x to the 7th being f, and this is my g function, the linear function down below. It's g times f prime minus f times g prime over g of x squared. So important things to notice. We have a derivative of the first and then the derivative of the second. This lays out a lot like, well, identically, to what I taught you on the product rule. And the reason I do the product rule in that order is because then quotient rule becomes really easy. Instead of the plus sign that the product rule has, it is simply a subtraction between these two. Okay? The other thing to note that's a little bit unusual is that we have g of x squared. No derivative of that g of x. It's just the whole denominator, g of x here, will be written underneath it in a squared term. All right, let's try it. Get my f and g back on here. Okay, so, I didn't see that I have an f function here. You know what, let's change this to an h function. Let's say h of x, so that we don't get kind of copycat functions going on here. So I'm going to call this h of x. H prime of x will be x to the 7th. I need to take its derivative. I'll multiply it by the bottom, 3x minus 2. Then it is a subtraction. Okay, got it. And it's the derivative of the bottom now. Derivative of the bottom multiplied by the top, x to the 7th, divided by the bottom, g of x, which turned out to be 3x minus 2 quantity squared. That is the layout for our quotient rule. What I haven't done is actually taken those derivatives, so let's process through doing our derivatives. We'll get 7x to the 6th because we took the derivative of that. It gets multiplied by 3x minus 2 minus the derivative of this term would be simply 3, thank you, because that's nice and easy, multiplied by the other function, and then over 3x minus 2 quantity to the 2nd. I almost wrote 7th. We are not going to FOIL out the bottom, but we will simplify the top. So let's go through and simplify. To do that, we'll have to do some distributing. So 21 x to the 7th minus 14 x to the 6th minus 21 x, oh, what's with the 21? Minus 3 x to the 7th. All over 3x minus 2 quantity squared. Simplify one more step. My h prime of x turns out to be 18 x to the 7th minus 14 x to the 6th all over 3x minus 2 quantity squared. There's your answer. You know, we could, I was just looking at this, we could have pulled out an x to the 6th. They also have a 2 in common, giving me 9x minus 7 over 3x minus 2 quantity squared. Another really good answer, right? A little bit more in factored form. Do we have anything different? Oh, talking about, I'm going to skip that other one because it's kind of the same stuff. Just follow the algorithm. This is a good warning. I think the quotient work is a lot of work. So if I can maybe avoid the quotient work, I will tend to do that. So don't think just because I see numerator over denominator that I immediately have to go into quotient rule. Not necessarily. Notice how this really is 1/6 times x squared plus 3x. This can be done by just a nice simple power rule. 2x plus 3, and then we could distribute this 6th, and I get 1/3 x plus 1/2. I think you'd all agree that that's a little faster than going through the quotient rule. This next one, remember these are the ones I just love. Love, love, love. Because I can take that denominator and break this into two separate fractions. So I'm going to distribute my 2 and write these as separate fractions. 2x cubed over 5x, I'll simplify that, and then I'll have 2x squared over 5x, and I will simplify that. Let's simplify, like we said we were going to. So we get y equals 2/5 x squared minus 2/5 x. No quotient rule? I love it. Let's go into our derivative, y prime. If it helps you write this out, otherwise pay attention to notation and you'll know you took a derivative. Power rule this, 4/5 x minus 2/5. No quotient rule. Oh, that also could be represented like this, couldn't it, since they have the same denominator? It's good to be bilingual or multilingual in math, isn't it? We can speak in different terms there. There's the homework. Hope this helps you guys. Good luck. If you still get stuck, you know, there's always the internet. You could Google and look for other videos on quotient and product rule. See you later.